Use the data in the table, which gives the position of a block connected to a horizontal spring at several times for a block of mass m equals 0.260 kilograms, and assume friction is negligible. A. What is the spring constant K? B. What is the maximum force exerted on the block? C. If you replace the block with a new block of mass which is 0.190 kilograms, which parameters along Xmax, Vmax, Amax, Fmax change, and why? Okay, to get general gist of what this motion is representing, let's take a look at this simulation. Well, because this is to get a general gist, we are going to set spring constant and mass to maximum. And the system we're considering is horizontal mass spring oscillator, as can be seen above. And when the block is pulled, as showing right now, it will oscillate back and forth due to spring, as you can see right there. Okay, well, let's get to the problem again. Taking a look at this data and problem, we can state that this quantitative problem deals with the concept of Hooke's law and Object-Spring-Oscillator. Some of our infos are given that amplitude is 5.4 meters and mass of block is 0.26 kilograms. Well, period is hidden information that we need to find. Well, in order to do that, let's take a look at the table one more time. So, going from 5.4 meters from negative 5.4, this one right here is not at one period. What we want to look for is one whole cycle, which is when the amplitude reaches the same exact point again, not in magnitude. So we can state that period is 2 seconds. There are several things that the problem asks. One, the spring constant K is one of the things that we need to find, and the maximum force exerted on the block. And third, what variable of those changes when the mass changes? Well, let's get to A. The equations that we were gonna need is the things that deal with angular frequency. Well, first, with the informations that we know, we can write that period is equal to 2 seconds, and we can get angular frequency from that equation, which is 2 pi over t, which means that angular frequency is pi itself in right here, because those 2's will get cancelled out. Well, because we know angular frequency, now we can derive spring constant from that formula, which is K over m. And if we square root both sides, should I change the pen? Nah, I think this is visible. Okay, we can state that w squared equals K over m, and we can leave the spring constant by itself by multiplying the mass by both sides, and now we can end up with the formula mw squared equals spring constant. Well, we know angular frequency, the one that we just solved, which is pi, and we can see that mass of the block is 0.26 kilograms. Well, let's plug the data in. Let's write the numbers just one more time to be precise. Okay, let's see, 0.26, 0.26 times pi squared. There's the value. Let's round to the hundreds, and then we can say that spring constant is 2.57. Now the second problem. What is the maximum force exerted on the block? Well, to find this maximum force, we need to combine two formulas together, which says that force in this system is equal to negative mass times amplitude, which is A, and W squared, the one that we just solved, with the formula cosine WT over plus 5, not over plus 5. The reason why there is negative in front of this force equation is because in this simple harmonic motion system, an object can move back and forth from the amplitude it started with. In other words, minimum and maximum amplitude is always the same in these systems, unless it gets damped. But we are in happy physics and for the sake. Alright, we want to find the maximum force, which will be the positive of the number that the formula will give us. So we know mass, we know amplitude, and we know angular frequency, and the rest part of the equation can be edited, and let's solve for that force. There's the number right there. Alright, and rounding again to the hundredths, we can say that the maximum force that the block has reached is 13.86 newtons. Now for the third problem. What variables will change? Well, displacement, first of all, is just about how far the person or anything pulls the block at the first time. Even the block's mass increases, how much that the block will get pulled will depend on how the person wants it. The mass change will not change the maximum displacement. Well, the maximum velocity has the property of angular frequency in the formula, which can be described by the square root of k over m. Well, as you can see, there is a mass in this system, in this formula right here. So as we can see, as mass decreases, we can say that the angular frequency will increase because it is in fraction. And then again, if mass decreases, the angular frequency will go up. Therefore, we can say, because angular frequency changes in the formula, that the maximum velocity will change also. And by the same reason, maximum acceleration will change also. Now here comes the concept of Hooke's law. What does Hooke's law represent? Well, the formula can be described by F equals negative kx. Well, from this formula we have that we don't have mass in this formula, right? However, someone would argue that, hey, k, the one that we just derived from the equation at the question A, the first one, we derive from here that angular frequency squared times mass is equal to k, right? Well, let me just write down this formula one more time, multiplying both sides. Well, now there is a mass in the right side of the formula. So if mass increases, won't spring constant be affected, so the force will be changed also? Well, let's rewrite this formula one more time. Well, there is mass right there, but what is angular frequency squared? Right, it is square root of k over m squared. Haha, now you guys are seeing what we're going out of. Well, squaring that just one more time will give us k over m, because that was initially at square roots, and those masses just get cancelled out, and the spring constant is just spring constant. Well, then what is this that exactly saying? Well, to put it in simple, it is saying that changing the block will not change the property of the spring.